Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about. It should be noted that in most of the valves that work in real conditions, the differential pressure changes when the valve opening varies, for which the real curve that relates the valve travel to the flow departs from the inherent flow characteristic. This new curve is called the effective flow rate characteristic. As the differential pressure variation indicated depends on the combinations between the resistance of the pipe and the characteristics of the pumps and tanks of the process, it is evident that the same valve installed in different processes will inevitably present different effective characteristic curves. Take, for example, a typical circuit of an industrial process formed by a centrifugal pump, the control valve, and the pipe. It is evident that the delivery characteristics of the pump and the head loss absorbed by the system will vary depending on the degree of opening of the valve. Here, we can see that the differences between the discharge pressure of the pump and the head loss of the pipe when the flow rate varies corresponds to the head loss absorbed by the valve, and that this increases when the flow rate decreases, expressing the pressure loss of the valve at its nominal capacity, complete opening, in relation to the pressure drop of the system, line plus valve. A coefficient R is obtained. The value of this coefficient will depend on the relative size of the valve in relation to that of the pipe. The smaller the diameter of the valve, the greater value of R, and the resistance of the pipe in relation to the assembly. The lower the resistance, the greater R. For each value of R, an effective characteristic curve can be constructed that will deviate from the inherent curve and will coincide with it when R is equal to 1, that is, when the line does not absorb pressure, and all is available for the valve. If the value of R were very small, the control valve would absorb very little pressure, and the inherent characteristic would be very distorted. To better understand the variation of R, we are going to analyze this system with constant total head loss. This is the case of a reservoir discharging to a lower level through a control valve instead of relying on a pump feature like the previous example. The flow rate through the valve is generally calculated with this equation. If we consider a pressure drop of 1 bar and we call the circulating flow rate kV, we will have this formula, replacing K times A with kV. By analogy, the flow that passes through the pipe is that of this formula, where K1 is the flow that passes through the valve with a pressure drop of 1 bar. That is, it is a constant. The effective coefficient of the valve that replaces the previous valve plus pipe assembly will be Ke. H would be the pressure drop, and Qi would be the inherent flow characteristic. Substituting everything, we will be left with this formula, and its maximum value will be the one at the right. Developing and substituting, we will be left with the final expression Qe, which is a family of effective curves based on the value of R and the inherent characteristic Qi. If R equals 1, the inherent characteristic is confused with the effective one. If the characteristic is linear, Qi equals to K times L, resulting in this formula. If there is a percentage characteristic with rangeability R equals 50, Qi equals 0.0250 L, then we would have this. The two families of curves are represented in these graphs. Here, we can see that the easy percentage characteristic gradually shifts towards a linear characteristic curve as R decreases. That is, as the pressure drop available to the valve decreases, and simultaneously, the percentage of pressure loss in the line increases. And well, this will be all for today's video. Don't forget to give me a like, subscribe, and share. I upload videos every Wednesday in Spanish and every Friday in English. Adiós!